Okay. Yeah. Hello, everyone. My name is Vivek, as you already know. My topic is WebGL and slideshow transition. So we'll talk about WebGL and then we more talk about how the transition 2D and 3D happens. So before we going further, let's talk about what is the WebGL. So WebGL is not any fancy things, but it's just a JavaScript API which allow us to rendering 2D and 3D graphics within the web browser using the GPU. So that's what the WebGL is. There is no magic happen here. So before we understand the WebGL, we should compare it to the normal 2D canvas, which is our normal HTML canvas you can consider. So let's talk about the first of all 2D canvas advantages. So the 2D canvas API is much easier to learn and use compared to WebGL. So as we go further, you will understand that WebGL API is not straightforward, but it's not that hard as well. But compared to the canvas, it's not straightforward, and drawing commands is quite simple in the 2D canvas. Now, everything comes with disadvantages, and that's what 2D canvases does. So the when we try to do something on a 2D canvas is mainly use the CPU, and which make it's quite slower when we have to do some complex transitions or when we do some complex rendering stuff on the canvas. That's where we choose the WebGL canvas. WebGL canvas is much faster as the shader code run on a GPU. Now I'll talk about more on a shader code later, but you can assume that that's a program is run on a GPU. That's why it's so faster. It's have a like lot of customizations and the visual effect and animation. You can do a lot of like bit more complex task or rendering task than the normal um, canvas. Frameworks like 3JS and Babylon.js is actually easy to learn compared to the normal WebGL or core WebGL. WebGL also have some of the disadvantages, and the development time is significantly higher compared to the 2D canvas. It's required to basics or some certain level of math understanding and graphics as well. For some, if you are doing some more complex task on rendering, and also some of the old browser might not support it, so you have to try to implement the mechanism which allow us to perform on a WebGL and fall back to the 2D canvas if browser is not supported. Now let's talk about the WebGL basics from here. WebGL, like we first to understand what is the shader. So shader is nothing but it's just a GPU program, which actually help us to rendering pipeline. So WebGL have a two shader. We'll see in the code as well later on in the demo that how this shader is being work. But for now, you can understand that every WebGL program have a two shader, and it's actually comes from the OpenGL. And OpenGL have a like a geometry shader as well, but that's doesn't support in the WebGL. Maybe in future they supported it. So in the WebGL we have a two shaders. So what the vertex shaders actually do is they actually handle the vertex position. So whenever like think of this way that when you are trying to draw something on a canvas, then you have to draw like when you have a pen and paper, then what you have to do is then you first do the vertices, then you fill the color. That's what you do in a pen and paper. That's exactly doing here. So vertex shader is just a vertex position. So every position is filled by the vertex shader. Vertex position, then WebGL rasterizations variable primitives like points, triangles, and then during rasterization, it called also the fragment shader. The fragment shader actually does the color of every pixels. So whenever you see the canvas on a color, that's done by the fragment shader. Both code will be written in the GLSL. This is OpenGL sharding language. Now, clip space coordinates always go from -1 to 1, regardless of the canvas size. So whatever canvas size you use, The clip pace is the -1 to 1. The clip pace is like you can understand the x, y, and z axis. So every x, y, and z axis coordinates from -1 to 1 will be there. Now this is the WebGL pipeline, you can say. So what we have is we have a three dots, and we don't know the position. Then we pass it to the vertex shader. Then they render it to their positions. Then primitive assembly happen through the vertex shader, and then that primitive assembly is actually draw that triangle. Now that rasterization happen and that pixel with fill with the primitive assembly, and then also fragment shader add the color for every pixels, and that's how you see the entire triangle on a screen of a frame buffer. Yep. Now uh, Now, in order to pass the data to shaders, there are four ways we can talk about here, and then we maybe go to the practicals. So one first is attribute and buffer. So buffer is a simple array of binary data. Buffer usually refer to the position and texture coordinates. We mostly use for positions. Attributes are used to specify how to pull out the data into the vertex shader. And buffer is not random access. Each time we execute the vertex shader, it's pull out the new data from the buffer and assign it to attributes. Uniform is again just global variables, you can say. It's you can pass it to both of the shaders. So and attribute is just for vertex shader. So that's what uniform does. Texture is generally for passing the image data or buffer of data. That's why we use the textures. Varying is a way to pass the data to the fragment shader directly without interrupting the vertex shader. Now every shader, we must calculate each vertex final position and assign it to the GL position for a vertex shader, and for a fragment shader, we calculate the color, final color to GL frag color. And for a new WebGL like WebGL 2, that's the older previously I talked about is for supported for WebGL 1, but for WebGL 2 we have a in and out, which is kind of I mentioned here that vertex shader for in is attribute and out for is the texture coordinates, and where in is varying and out is the GL fragment color, and we'll see in the program that how it's gonna works. Yep, now it's demo mode. So I'll show you how actually the simple rectangle we can draw on a WebGL canvas, and then maybe we can go to our main code base. So yep, so this is a just a canvas, and we have a yellow color rectangle, and we have to check from here. Yes, so this is just a normal HTML. We have a canvas here, and I just add the script. Now what we have to do first is we have to extract the WebGL context, and I have extracted here. Then we have a vertex shader. Now as I already told you that we have attributes and uniform that might be go out of your head because you didn't see this program, but we'll come to this program later. But you can just see that attribute is just setting up here, which is a position. So we set the position to vertex shader using the attribute, and we shade the colors using the uniform fragment shader. Now what we have to usually do is we have to create the program. So first step is always to compile the shader. So we have to create the shader and compile it using this create shader function. So you can see the here we are compiling, creating the shader, and then compile the shader, and if it is an error we show it to the null. Again, this is just demo program. Ignore the code. I just write for you to understand which like much more easier way. So that's why I wrote it. The fragment shader similar way. So as we have first we have to compile both of the shaders. Then we create the program including the both of the shaders. So you can see the here we are creating the program and then attaching the both of the shaders and the link to the program with the current GL context. Then what we have to do is we have to look up the attribute and uniform locations. So as now we go to the vertex shader program, that now vertex shader we are passing the attributes, and the in the fragment shader we are passing the uniform that we have to attach here. So here I actually there is a two methods that actually help you to attach the program, and then we will use this position location later on. Now we have to create the position buffer. Now what is the position buffer? So in the canvas, where do you want to see the your object? That's what the mean is to position buffer. So as I already told you, right, the clip space is from -1 to 1. So here I have explained so this is the y-axis and this is the x-axis. So now how I have created this buffer is I have created a triangle of 3 3 points. So you can see these 3 points is actually confirm this one, and this one. And these 3 points actually confirm this one, and this one. So this actually include two triangles into the rectangle. So that's how the rectangle is being informed here. Then what we have to do is we have to pass that into buffer, and we have to clear the color and viewpoints to our entire canvas height. And then we have to use the program into a particular GL context, and then we set the vertex attribute object or vertex attribute array, and then we have to pass all the parameters like how many components is being passed, data type as well, from where do you start your buffer, and all these parameters to accessible to vertex attribute. And then we can obviously pass the color because we have a access to uniform that I already told you that uniform is we have accessible here that we using here, and then we can set that uniform from whatever value you want. So if you change here to 0, that actually change your color of that uh, particular rectangle. And at the last we draw the triangle and with 0 to 6 vertices. Now let's talk about the shader program. So what we do in the shader program is we accept the attribute. So at the first, always for every pixels vertex shader is executed, they accept the position, the current position of the of the array, and then we have to return the GL position. So where do you want to present? Now if you don't like in the current say vector 2 is this is called as a vector 2, so it's have a like two parameters x and y. But if you don't have other parameters, you can pass a 0, and a fourth one is always 1, and then that's actually pass as a GL position to vertex shader. That vertex shader will decide to where to this put this particular rectangle. Now let's talk about the fragment shader. The fragment shader actually accept the color, and that color is actually passed into the GL frag color, which actually decide what to put the color in this particular in the particular sections. So that's how the entire WebGL program is running. So do you have any question till now? Because now the complexity will increase a bit more. So if you don't, if you have a question, then please ask here itself. Nope. Okay. Uh, Okay, cool. Then we can go into the transition. So we can consider each slide as a texture. So how we do the transition, that's we discuss here. So we are creating each slide as a one texture, and the current slide is as a living slide, and the next slide is the entering slides. The fragment shader use the both texture and render each pixel based on the time dependent mask, and we are using the time based mapping, which actually pass through the time uniform, and which time is from generally from 0 to 1. So this is actually considered as a progress of transition to 0 to 1. The shader may adjust to UV coordinates, and based on additional uniforms, direction to be determined which part of the screen show the entering slide and which part of the show the leaving slide. And we'll see this UV coordinates in the code as well, in the 2D code. And depending on the transitions, the shader decide the pixel using the function like mix and conditional logic we can maybe use for some of the transitions. And that's how we decide that entering slide, when to show the entering slide, when to show the living slide and transition effect. WebGL doesn't support the native text rendering. To render text, we typically, like for our case, we typically use the off-screen 2D canvas and then render a text and then extract the texture out of that off-screen canvas. And we combine those layers into the WebGL canvas. And that's how we render the text, and that's how you see the text here. Cool. Then let's talk about the 2D transitions in the code. Just opening. Okay. So in the code base online side, we have a class called a 2D transition, which is actually most of the 2D transitions are based on this class itself. So what we do that we'll discuss about here. Yeah. So the 2D transition is actually dependent on a transition base class. So this is a, like just a format class that we have a start transition method, end transition method, and release resources and all, just a format method. But the main thing happens here. So here so first thing you have to understand is that for most of the 2D transitions, and in future if you are implementing new transitions, for most of the transition we don't need to change the vertex shaders because vertex shader remain the same. Our slide will be remain the same at the same position. We just change the fragment shader, which actually change the color and which actually decide to what to see on the display, and that's based on that we are actually rendering the entire slide. So here you can see this is a classic fragment shader. I mean, it's not for every transition we have to write. For every transition we have to write maybe custom fragment shader code or maybe just get mask function. uh, so what we have to do is this is actually the written in a WebGL 2.0. So we have to mention the version as well and the precision of a float or medium in the medium p, which actually decide that the float should be for certain numbers after the dots. Then we have actually decide that. So yeah, so this is a general case, like this class is written for a general case. So it may be possible that we have just only one slide for a first slide or for a last slide. We don't have any other slide. So in that case, how to perform the transition? Not only that, but when we have to let's say want to load like loading animation or these kind of cases also defined here. So do we have a living slide? If we don't, then we have to handle other cases. We are handling the alpha as well. So what we initially do is we just extract the texture of living coordinates, and if the stride transition, then we living coordinate. Otherwise, we fill out for the specific color. Yeah. Now let's talk about the buffers. So this is how the buffer is being setted. So for this reason, we are getting from a 0 to 1 buffer. So we have to convert into -1 to 1, as I already told you. So the clip place is -1 to 1. That's why we set it to -1. The main function is this render function. The render function is actually decide what to do on a render of the program. So if you see here, so they extract the context. I mean, these are the just uh, variables which actually decide that is stride transition or not, and is it disposed or not. Uh, then we have just a GL context. Then we set if it is a slide transition, we clear the color, because if it is not slide, then we should clear the color, and then clear the entire canvas. That's what here this particular piece is done. And then we use the program bind the vertex array object, and then we use the time to as a uniform for a latest time, whatever the rendering is done, the time we are using. And we bind the texture of living slide first. But if it is not a slide, then what we have to do is we have to set the colors, alpha, and other stuff, whatever is required. And then we bind the exiting side, sorry, entering side, which is to the, like, we bind the texture of entering side. Then we render the uniform values, and then we bind array object. So and then draw the triangle of 0 to 4. And this is a different code. So yeah, so that's what pretty much we do for us simple 2D transitions. If we look at the some of the example, maybe maybe we can do circle. This would be easier. Yes. So here what we do is, so we extracted all the other things from the parent class. So clipping transition is almost done the similar, but they have like some certain cases where we have to handle what things. Mm, Yep. So here you can see the fragment shader is become much more complex for this case by explaining this stuff. But here you can see the get masked function, which is passed from here. So what the get mask function is does is here is, if you can see, if I'm trying to explain the shader code so that you can get an idea that what actually shader is doing, maybe some certain key, certain level. So what first we do is we actually accept the UV coordinates. So we know that where we have a um, current positions, and we also get the time, which actually help us to identify the progress. Now we have a center. Now we first find the center. So for now this case we have a, like, for all this 2D case we have a buffer from 0 to 1, and later on we converted into -1 to 1. But for now the center would be 0. If we consider 0 to 1, then the center would be zero point 0.5 to zero point 0.5. And then we find the distance, then we find the progress size, and then we step function, which actually decide which one to pick. And minimum, so let's say if I have a completed one, then we return the mask as a 1, otherwise we return the mask as 0. And now we see that what the mask will do here. Yeah. So yeah, so you can see yeah, so get mask value is here. So the mask will done, and then we, based on that, we decide the which texture to perform, and how the color should be look like. So yeah, this is pretty much and also in the WebGL2 the out color is used because we, as I already told you, we use in and out. You can see we text coordinates is going in, which is come from the vertex shader, and out color is actually used for chaining out the color. This is pretty much happened to all the sorry all the 2D transitions. Mm, Now let's talk about the 3D transitions. So you see the static noise transition. We'll talk about that as well. For most transitions, we perform the operation, like for the 3D one, mostly we perform the scaling and rotations on a primitive 3D space. For 3D transitions, we need to create extra helper for some of them, and which is we see in this particular case. So in this case, like we don't go with the just two texture, but we, in this case, we need a three texture. And the middle texture is, you see the dotted, black dotted, randomly generated permuted data. A multiple Transformation metrics like projection, model view, sense, primitive, and operations are used to position and animate the slide in the 3D space before they are actually blend. So, what are the projection metrics? So these are the five terms that's actually in the 3D graphics concept, but I'm trying to understand, like explain you bit more on a easy language. So this think of this as your camera lens, and it takes the 3D world, what is in front of your camera, and the project is onto the flat screen because the perspective object further away appears the smaller. And this is the good example. So you have a, like, let's say you have somebody stand in a queue, then from side you see that further away objects looks very smaller and keeps getting smaller as they go the further. And that's what the projection matrix does. The model view matrix is the matrix positions and oriented the entire scene relatively to the camera. In other words, it's like setting the camera viewpoint. If it were missing, then you will always see the view is fixed and static. So it's actually the camera angle that's decided by the model view matrix. Now, scene transform matrix. So this apply to adjustment to you want to make for the whole scene. So if you let's say if you want to recenter or scale entire scene on a 3D space, then you can use this matrix to see in the transform. Primitive transform matrix. This one works on an individual object, and this will primitive within the scene. It transform like moving, rotating slide without affecting the other objects. Now, operation transform matrix. This matrix is used for the animated effect and the change over the time. So it's basically done the operations over the time based, and it's actually done the operation that we provided. Let's talk about the 3D one as well. The code. Yep. So 3D is quite similar to 2D, but the fifth five thing I already told you is different. So there is a class called 3D transition, which is here. Yes. Now this is a base class for 3D transitions. Obviously, it's dependent on other class as well. But here we are enable the blending and do the alpha blending. This is the vertex shader of 3D transitions. So here you see the all five matrices that's we have. And don't confuse by this code. This is just a transform code. This is just an inverse matrix. So don't confuse by that. But the code is here. Main code is here. So we are passing all matrices dot product, and then we custom transport the particular result, and then we pass as a texture, and then we pass normalize with the v normal, and then v normal we are varying into the fragment shader. Now in the fragment shader, we actually accepting the v normal, which is again the coordinates, texture positions, it's also the coordinates, and the slide that we want to perform these transitions. Now also these are the calculations that's happen. I mean, it's not so you can read this code. It's not like it's not a that way. This init uniform is basically done the uniform initialization. So initially we create this type of matrix for every view, and you can see then later on we change based on a requirement. For a rendering perspective, and in the render function is again this is important because every time this rendering is happen, above code is just executed once. This rendering function actually first clear the canvas, set the viewpoint and clear the canvas, assign it to program, then actually bind it to function, and for a leaving slide texture to the texture, and entering slide texture to the texture one. So we have two different textures using, and then we render the uniform values, bind to vertex array, and which is a VAO, and draw the triangle on the screen. So this is pretty much we do, but you don't need to worry about these things. For most case, like we'll see the cube transitions, which was easiest one, and you will understand that it's not, because we have a created operational matrix. So now whenever you want to write 3D transitions, you just need to see, for a most case, it's not a standard rule. For a most cases, if you want to like moving the object on a 3D, just like left and right and up and down, then this will be works. So in the cube transition, this is the logic of cube transition. So here you can see we created the first primitives, and this primitives is actually the triangle. You can see this is first triangle, this is the second triangle. So we pass as a triangle and push at a triangle on a 3D space. That's what the difference here. And that's the push triangle method does. Then we have a living primitives. And what we do is we push just living primitives into the slide. Clone deep, it means they just send this slide copy, which will never change on a so if slide is changing. Then what we do is we push the operations. So here you can see we created the make, rotate, and scale depth width. So this is a operation we created inside this operation folder. You can see we have 5 operations, which actually does like scale is does scaling, transform it does translate, rotate is like rotating, and all this 5 operations, and we just perform the operations here, uh, and we just push that operations with appropriate value. So you can see what we have to pass. We have to pass the axis, origin, the angle, scale, and other variables like mn20, which is from where to where. So this is from 0 to like time, which time to which time. That's what the mean is. So that's what we have to pass in the every functions and every operations, and based on that it pick up the operations. So what they do is they initially first perform the living primitives, and then perform so first it perform the operations. So operations is defined here. So you can see operations is defined here. So what we have to do is operation is applied to all entire scene. It's not for a particular primitive. So assume like a primitive is entering slide and leaving slide, right? So think of this way, like primitive entering slide and leaving slide will the entire scene is affected by this operation. And I already mentioned that the operation matrix is responsible for this operation. So what they do is they scale out. So if you remember how the cube transition is happening, so first we have to scale out from a 3D point of view, and then we have to again go into scale. So basically zoom out and zoom in our language. That's what I was doing here. So and this primitive transition is applied to that particular primitive itself. So we are need to rotate and scale for a bit. So that's what we have to do for a living slide, and that's what pretty much transition is done here for 3D. And I mean, you can check it out other transitions as well, helix transitions, and most of the transitions is done this way. There is there's base class of simple transitions which actually apply to here, and if we look at how the operations is handled here. So you can see the call is so first is the call is here. So you can see display slides, which actually call initially, and then they display. This is called from a render function, this function. If you want to see yeah, here you can see the render function called the display slide. What they do is they apply the operations first that we decided on that particular metrics, and then it's render the texture 0 with the living primitive, and then same apply for texture 0, same texture they're using, but again the fragment shader will decide which part to execute for on the screen, and they again use the slide texture that we have passed in a fragment shader. So yeah, this is pretty much happening in the 3D transitions. uh, Uh, till now, do you have any question? Anybody have any question? Then please ask. Okay. Then we can go to the WebGL tips and tricks. So if your browser doesn't support, then we have to go to the fallback to the 2D canvas, and we can check using get.webgl.org. Spectre.babylon.js is Chrome tool and Firefox tool, which actually help us to identify the WebGL states and diagnose errors. So if you are writing code, shader code, maybe you can try it out. And whenever you are like playing with this WebGL code and you forgot to pass uniform and attribute, you might go into some wrong state that causes an error, and that might not be shown in the console as well. So keep in mind that your uniform and attributes are properly. There is one state change diagram which I love to see how the things happen in a background. So if you go to this website, I'll paste the link in the chat of TTT channel in Bettermost. So if you go to this website, this actually have a like 4 or 5 like these many programs, and these programs actually help us to understand how the particular WebGL context is being created and all that stuff. So you can see I'm fast forwarding it, and it shows that how the buffer is being created, how the texture is loaded, how the map is using, and how the vertex array object is used here, and you can check the global state as well. So this is good for beginners. If you want to try it out, you can check it out that how the particular piece of code is working on a some, and this is canvas, so you can see this is the result, and you can try it out, maybe some simpler as well, some triangle, or smallest one. Yeah, smallest one is just this. So this is just color, so they just use a color on the canvas. So you maybe try it out, this tool, this is useful tool. And yeah, at the last, thanks to the amazing engineer Quickie, Marco, and Simon who did this work entirely. And yep, thank you.
Thank you, Vivek. Now it's time for questions. Arsh, Andrash, Attila, questions?
No, thanks.
No questions, thank.
Okay, Benobe, questions? Benobe? We can't hear you. Maybe you can type. Kellen?
I just wonder, when doing OpenGL transitions on the desktop, it's always a problem that the individual drivers there's something wrong in somebody's driver. So if we're doing it through the web, are we released from that problem entirely? Do you just not have to worry about it, and it's the browser's problem to figure out if it's going to work or not?
Yeah, so that's a good question. So for a WebGL context, it's actually doing all the browser thing. So browser will decide to that this does this browser have a this sufficient driver or not. If they don't, they just fall back into the error. So that's also dependent on the browser itself. So I mean, we shouldn't worry about.
Yeah, great, thanks.
at least WebGL is a subset of OpenGL.
Yep. It's a subset of it.
And it looks much like a much more modern GL, like GLES, something like this. I assume it's thrown away lots of the horrifying. Hopefully, it's implemented on top of Vulkan, but you never know.
Yeah.
I thought it was a really great talk, though. Thanks for very detailed, lots of useful stuff. I love that debugging tool. And yeah, I wondered two things. I think, well, three things. The first is shaded compilation. Fires up essentially Clang in the background and does some amazing things with these really weird architectures. And it seems generally to me to be optimized by ricers for creating hyper complicated game-based shaders, none of which we really care about. I think if we didn't optimize our shaders at all, and we used, the quickest, dirtiest compilation, we would still have plenty of hardware support for our transitions. But but we then pay this huge cost for this hyper optimization part. I was wondering if we compile those ahead of time, or whether we can anticipate that there's a transition coming up, and while the app is quiescent in between transitions, then do those compilations early, or how does that work?
Yeah, so I have a ticket for that future enhancement. So basically, our idea is to compile the shader previously through the web worker, and then each use for each slide, which we have to pre-compile the entire shader. But we have to test it out. I'm not sure how it will be going. So.
Sure.
Yeah.
But I mean, I don't think that we need anything terribly complicated there. Your average slideshow is show a slide and then talk about it for at least more than a few seconds. And I would assume that once we're quiescent for a second and the slide's up and the transition's over, compiling the next one makes a lot of sense, right? Like I would hope it's easy enough to do that, and without a clever and something else, which whether threaded compilation actually works in drivers, I don't know. I'd be suspicious that it doesn't. The other thing is that clock wipes, I still have very slow clock wipe. I just wonder how the animation timer tick thing goes. Like my clock wipe goes like that. It's not smooth and fluid. Maybe you can show me one if you've got one there.
Clockwise?
A clock wipe, as in it moves a thing like a clock hand round and reveals the other. Maybe it's a wheel. You call it a wheel.
Yeah.
Call it a clock wipe. So yeah, can you right like that, and that. What I would expect is a smoothly moving, line, ideally anti-alias between the things that reveal the other one. Yeah. I don't know why that is. Is that, I mean, the GPU can do that incredibly effectively. It just looks like there's some kind of rounding, or I don't know what.
Maybe we not wrote the efficient code.
No, I don't believe that. It's incredibly trivial blending two things. Like the GPUs are so powerful, it would be hard to write code that was slow on the GPU, I would think. It looks much more like we're not passing a parameter or a proportion into that properly or something. I sorry to report my bug in the
Yeah, I'll check it out, this code, no problem.
Yeah, but fair enough. Step mod angle slice. Yeah, who knows? Hussein. Shoot, sorry, go for it.
Hello, and thank you for the presentation. Should it be something like GL rotate or something? And is it something, I'm not familiar much with the shaders, but as far as I remember, there was something like GL rotate primitive that you could pass, and it was rotating things smoothly, but yeah.
Yeah, I think the thing there is that you don't actually rotate it. You just transition between one thing and another at a different point. When I designed hardware for this in the past, we would have a pre-rendered clock wipe mask that we would use to alpha blend one with another, and you would essentially just increment the place in the mask that you were at, or and that gave a very beautiful, incredibly smooth result. But I think modern GPUs can do the same thing rather trivially. Yeah, and with the pixel shader, we should be able to get rid of that jaggy edge as well and make it beautiful. But there you are. Last question was, should we use this for our tiled rendering? But I think that's probably a Chris question, isn't it? Like, so instead of rendering the document pane with a 2D canvas, we could potentially use a 3D GL canvas, but maybe that's a bigger discuss with the browser expert. I suspect that we're using the accelerated GL stuff underneath anyway.
But yeah, my point of view is like we don't support, like WebGL doesn't support text rendering out of the box. So
yeah, we don't use that text rendering anyway. So, but yeah, I suppose so for overlays and things.
Okay, yeah, then
thanks,
maybe we can.
Sorry, I jumped in early. I jumped the queue. Anna, you were working through people with diligently.
Yes. Okay. Jaume, João, Justin, questions? No questions. Okay. Miklos, Mevan, and Marco.
Yeah, the question, it's now we have transitions between slides. Another thing that's nice in other presentation programs is to have transitions within slides, well, animated transitions within slides, like showing an image, different image progressively, or chart animating or something like that.
Yeah.
Well, I'm just wondering, what can we do with that? Or what formats could we improve support for so that we have such features?
Yeah, I mean, so you are asking about the animation, how it does, right? Or am I misunderstand the question?
No, well, rather, what are the opportunities to add more transition and in-slide transitions?
Oh, so
mostly for format, and then implementation should follow. But first, are there some that we want, or it's rather a wide question, open question, rather than anything.
Okay. So I don't understand properly. Maybe I'm not getting your question, but what I get is, yeah.
The question, Vivek, I think, is about animation in slides as well as transitions. So really two types of moving things. And I think we do use GL for animations.
Yep. Marco did that work.
All right, I'm just coming too late to the party.
Yes, I don't think we do it for like pie charts that change proportions as they. I think that's kind of some elite stuff. But in terms of moving text and flying things in and that sort of thing, I think that's all there. But Marco, are you over to you? Go ahead.
Okay, thank you, Miklos.
I would have one question if Marco doesn't want to talk about animations. Okay, I will just go ahead with my question. So you mentioned that WebGL may or may not be available, and if it's not available, then you fall back to these 2D canvas. So what happens in that case exactly? Is it like the browser is providing us the very same API, and it will do everything in software, but you can still work with your shaders and or does that mean you just don't have slide transitions when WebGL is not there? Like, how do we behave in Cobra Online?
So what we do is we first usually try to run the basic shader code, and when we compile the shader code, if driver is not exist, then it will go into catch case. I mean, it's not compiled properly. So that's how we get to know that this device is not compatible with the driver. And you can see in this slide rendering logic, we are using this slide render 2D. And if we find this, like we first render this basic program. This is just a simple program. If we are not able to load the texture on the WebGL, then we fall back to the normal canvas. That's what we do. That's how we figure out that this browser is supported or not.
Thanks. And then do you have to implement each and every transition 2 times, one with the Canvas API and one with WebGL, or is that automatic, or we just don't implement the fallback, or?
No, so we initially we when we are like rendering the slide, initially we decide that this user basically supported the WebGL browser or not. So we don't have to worry about the each and every transitions. So initially, if we decided that, let's say this is supported for WebGL, then we go to the WebGL transitions. If it's not a supported WebGL, then we go to the normal 2D canvas transition we have. That's what we implement.
Oh,
That's
really?
how.
Okay. My hope was that we were going to get rid of those 2D transitions, the SVG stuff, and kill it completely.
But we can't kill because let's say if browser is using very old browser, like
yeah, but we
very
don't care about that. Very, very old
yeah.
browsers are a nightmare to support, and I would much prefer to have less code, less maintenance, less bugs, and more debuggability. I think it would be better to fall back to cuts, straight cuts, no transitions if you don't have WebGL, I think.
But if let's say if like the problem with that case is, let's say we are everything rendering on a WebGL canvas. So if WebGL is not supported, he will not able to see the slide.
No, of course. Absolutely. But I just don't want us to be supporting the SVG animation and transition thing. Let's have just plain cuts. We just show the tiles on the canvas or the images on a canvas if we can.
How old a browser would one have to have for WebGL to not be supported?
I mean, you can find the state on the internet. It's very small. I didn't check anywhere time.
No, I think it's very tiny. My
Yep,
expectations should be everywhere. So yeah. So I think I'm just more interested in optimizing for maintainability and development rather than worrying about SVG fallbacks. Marco, are you with us, Marco? Are you just muted or?
Yeah, I'm here. Yeah.
Oh, cool. Yeah. So what are we doing for the fallback there? Do we implement a very cut down, simple cut-based thing? What do we do for the animations? Or are we still using the SVG thing?
No, we are not using the SVG at all.
Excellent.
Except is a setup to use it at the server level.
Yep. Okay. So we have a simple fallback then that does 2D canvas stuff and shows the same.
Yes.
Okay.
As I wrote, if we needed to use the 2D canvas, transition are skipped, and we are able to run some effects animations, but not all.
Brilliant. Okay, I think that's where we should be. Just keep the code simple. Nice. Does that help, Miklos? I mean, it's a great question.
Yeah, that was my question. Thanks. I have a very detailed answer. Thanks, Vivek and others.
Okay, thank you. Part Pedro, questions?
No questions, thank you.
Pedro? Okay. Raj? Skylar?
No questions, thanks.
And Tomasz, do you want to add something? I guess no. Okay. Thank you, everyone. Thank you, Vivek. I see you next week. Bye-bye.
Great talk.
Bye.
Thank you, everyone. Bye.